Hello my people, I hope we're doing well. This is going to be the last video on this unless it is requested that I make more. Let's go ahead and get started on this first one. Now, some of you might be sitting there thinking to yourself, gosh, I really wish that instead of 1 minus cosine squared, that was 1 minus 2 cosine squared, it was 1 minus 1 cosine squared. Okay. Well, why don't we turn it into that? 1 minus cosine squared x minus cosine squared x. Can I do that? I don't see why not. And then I can take that and turn it into sine squared x minus cosine squared x. Okay. Well, I tell you what. Why don't we, let's go ahead and multiply this by secant squared over secant squared. And when I do that, what happens is I'm going to get tangent squared x minus 1 over secant squared x. And then, of course, we get tangent squared x minus 1 over tangent squared x plus 1, and that is exactly what we have on the other side. Now, that is a reasonable way to do it. Of course, the difficulty is in this step right here and coming up with that strategy to do that. Okay? So let's see if we can do it another way. Okay? Let's 1 minus 2 cosine squared x, and we recognize that this right side has an interesting structure to it. Okay? And the thing is that right hand side is more complex anyway, and by our guidelines we probably should have started with that to begin with. Now, when we look at that right hand side, that bottom, that denominator can be turned into secant squared. And whether you turn it into secant squared or not, you could go ahead and just multiply by cosine squared over cosine squared. And if you do that, you wind up with sine squared minus cosine squared and sine squared plus cosine squared. That denominator looks familiar. I know that it's 1. And therefore, I have this. Well, I've already determined that this and this are the same. I just did it in the reverse order this last time. Because sine squared can become 1 minus cosine squared. And then you just subtract the other cosine squared. And I get my verification. Check. Okay. Now, I mean, there are subtle ways that you can do this in a little different way. Like I said, you could have taken that original and turn that denominator into secant squared. Well, if you're dividing by secant squared, that's the same as multiplying by its reciprocal, right? And then, of course, that becomes sine squared x minus cosine squared x. And we see the fact that we've seen that before, right? And so this is really just a slight variation on that second way to do it. All right, let's go ahead and look at the problem at the bottom of that page. All right, well, the right-hand side, I see the fact that the right-hand side is definitely rational, but the left-hand side has 3 terms. And the right-hand side has cosine squared, and that cosine squared can certainly be changed into 1 minus sine squared. And that 1 minus sine squared I know can be factored as the difference of 2 squares. But I also see this over here on the left-hand side. And I know that that's also a Pythagorean identity, and that can be changed into that. Now, we can probably factor out a GCF. The question is, what is the greatest common factor? And that's kind of a trick question, because you see, tangent x, secant x, is the same thing as sine x, secant squared x, right? If you were to sort of let this secant borrow the denominator, the implied denominator of tangent, because this is basically sine over cosine squared. This is the same, okay? And so you can factor out a secant squared and just get 1 plus sine x. Oh my gosh, that means that 1 plus sine x over cosine squared is equal to 1 plus sine x over cosine squared. There's my verification. Now, would it actually have worked to take this right here and reduced it and turned it, because remember when we were talking at the very beginning, this can become that. Well, is that helpful? Not really. Unless you can wind up figuring out a way to get rid of a whole lot of factors over here as well. Basically taking this and getting it 1 degree more depressed doesn't really help you to, I mean, you can do it that way. It just winds up being a little bit more roundabout kind of way of doing it. But I digress. Let's go ahead and let's move on to this. Okay. Now, this problem, secant squared plus tangent squared, is equal to 1 minus sine to the 4th times secant to the 4th. Okay. Let's try and figure out exactly what's going on here. Now, I recognize the fact that the right-hand side is more complicated because it's 8th degree. And 8th degree is a little bit more complex than 2nd degree. But what I should recognize is the fact that that right there factors as the difference of 2 squares. And this secant to the 4th, let's go ahead and sort of chop that up into secant squared and secant squared. And the reason why I'm doing that is the fact that that right there is going to cancel into 1. And I'll go ahead and I'm going to go ahead and take this secant squared and put it together with this 1 plus sine squared, and then show that this 1 minus sine squared becomes cosine squared, and when it gets multiplied by this secant squared, it becomes 1. At which point you can distribute this secant across this binomial, and you get secant squared plus, well, secant squared is really 1 over cosine squared, and when that's multiplied by sine squared, oh my gosh, will you look at that. Now, this is one of those where it really is not going to be helpful to start with the left-hand side. It's just, it winds up being way too much. Okay. And I'm not gonna deal with different ways of doing that one. Let's go ahead and look at this next one. You have what some would consider to be an absolute nightmare going on the left-hand side of that identity. But you notice that both of those rational expressions, both of those terms, have similar structures. Okay. And you know that if you get a common denominator, you're actually going to be, if you get a common denominator, you're actually going to be creating the difference of 2 squares in both of those numerators. So let's go ahead and do that, okay? Let's multiply, and I can't put it right next to it. I want to leave myself a little bit of room here. Let's multiply it by cosine x minus cosine y, or sorry, no. Okay, let's actually do it on the next step. We're going to have cosine x minus cosine y over sine x plus sine y. In order to get a common denominator, I'm going to multiply it by this denominator over itself. Right? And the hope is that I won't even really have to deal with much, because if this is 0 over here, it doesn't matter what the denominator is going to be. It matters that it's like that all the terms in the numerator are going to cancel out. Okay? That's our hope. And I'm going to multiply this one right here by this denominator over itself. And that product and that product, I'm talking about just the denominators, are going to create your common denominator. Well, let's go ahead and look at the numerator then. That's going to be cosine squared x minus cosine squared y plus sine squared x minus sine squared y. And you're thinking to yourself, how in the world is that going to cancel? Well, that's going to cancel because of Pythagorean. Okay, I just have to decide which one I'm going to change. Am I going to change the cosines or am I going to change the sines? Let's change the cosines. This winds up being 1. This cosine squared becomes 1 minus sine squared. And this cosine squared becomes 1 minus sine squared of y. Okay? And then you get sine squared x minus sine squared y. And you notice that when you distribute this negative, this sine squared y is going to be positive, and that sine squared y is negative. This sine squared x is negative, that sine squared x is positive. And what you get is you do get 0 in the numerator. And if you get 0 in the numerator, then it's equal to 0. Sine x plus sine y, and that is a whole lot of scribbles just to watch everything fall out, okay? Whew. Alrighty, let's have a little fun with 2 challenging problems, okay? These last 2 are going to be a little bit of a challenge just because, you know, I want to show you ones that kind of go beyond the normal fare. I just think that makes things a little more fun. And of course, if you can understand the really, really nasty ones, then you will be fine with the ones that are a little more common fare. Now, I have 1 plus cosine x plus sine x over 1 plus cosine x minus sine x is equal to secant x plus tangent x. And I know what you're thinking. You're thinking to yourself, gosh, that's a trinomial over a trinomial. If only it were a binomial over a binomial, I would have a prayer of simplifying it. Okay, well, what do you say we actually turn this into a binomial over a binomial, or at least make it functionally behave like one? And that's all we have to do. If we do that, then 1 plus cosine may be 2 terms inside the parentheses, but once we have grouped them like that, that numerator can functionally be treated as a binomial, and that denominator can be functionally treated as a binomial. And I can actually multiply by the conjugate. Okay, and I'm going to multiply by the conjugate of the denominator over itself. And just to make things easier, I'm going to keep things in their nice and neat little packages, okay? And so this is going to be 1 plus cosine x squared plus 2 sine x, 1 plus cosine x, plus sine squared x, all of that over 1 plus cosine x squared minus sine squared x. Okay, well that's fun. Let's go ahead and see. I can basically turn this sine squared right here into 1 minus cosine squared x. Okay, now that's helpful because in that denominator right there, I can actually, let's go ahead and rewrite that numerator. This has a 1 plus cosine, that has a 1 plus cosine, and so it can be factored out. Now if I factor it out, I'm left with a 1 plus cosine in that first one, and a 1 minus cosine in that second term. That down there, those ones cancel out, that negative is going to be distributed, and what you're going to get in that denominator is 1 plus cosine x, 2 cosine x. Okay, well that's all well and good. Let's go ahead, I tell you what, let's go ahead and distribute, okay? Now let's go ahead and just multiply this all out. I'm going to get cosine squared x plus 2 cosine x plus 1 plus 2 sine x plus 2 sine x cosine x plus sine squared x. Whew. Now, that looks like a whole big mess, but notice that this term, and this term all have 2's. Well, that's significant because this and this together make 1, and that can add to that 1, and so actually all of them have 2's once you actually combine those three terms, right? Because cosine squared plus sine squared plus 1 is going to be equal to 2. And so what I have here is 2 plus 2 cosine x plus 2 sine x plus 2 sine x cosine x, and guess what? That numerator factors by grouping. Okay. Now, you can get rid of the 2 because 2 is going to be a common factor of the numerator and a common factor of the denominator, but let's wait on that right now. Now, I'm going to group these. The common factor here is 2, 1 plus cosine. The common factor here is 2 sine x, and I'm going to get 1 plus cosine. Okay, almost forgot the x there. 1 plus cosine x, and then 2 cosine x. And what I get in this numerator is I get 1 plus cosine x times 2 times 1 plus sine x, all of that over 1 plus cosine x times 2 times cosine x. Well, you should recognize the fact that all of that cancels out. And I've got news for you. When you separate that fraction, you're going to get secant plus tangent. So you get secant x plus tangent x. And I tell you what, that was several different steps, but, and there may be a way to do it in fewer steps than that. That's the first one that I saw, okay? And if you want to give it a try and see whether you can solve it in another way, by all means, please give it a try, okay? Now, I promised that we would be coming back to that other problem that I found to be a little bit more difficult, and so I wanted to save to the end. And this one is even more of a nightmare than this one. All right. Let's go ahead and take a look at that. Doesn't that look fun? Now, you might be thinking to yourself, I tell you what, I'm just going to change it all into sine and cosine. That just seems like the best way to go, okay? Obviously going to be starting on the left. I'm like, okay, well, let's turn it all into sine and cosine. I think that sounds like a bang-up idea. Okay, and basically I've turned it into the implied complex fraction. Okay, well, if we have complex fractions, obviously we've arrived here because we want to get rid of the complex nature of that fraction. Well, this right here, I got to multiply by cosine over cosine in order to get rid of that. And I got to multiply by sine over sine in order to get rid of that. And the same thing here, just in opposite order, right? I need to multiply by sine to get rid of that. And I need to multiply by cosine to get rid of that. So when I multiply both of these, okay, multiply both of these by sine x cosine x over sine x cosine x, okay, what happens is I'm going to get sine squared x over sine x cosine x minus cosine squared x in that first one, right? Take a second for it to sink in, because when I take this and multiply this, the cosines are going to cancel and the sines are going to combine. When I take it to the denominator, I have to distribute it, right? And when I distribute it, that first term times 1 becomes sine times cosine, and when I take it to the second term, the sines cancel and the cosines combine. Well, something similar is going to happen in this second one, except for sort of an opposite way. And I'm going to get sine x cosine x minus sine squared x. Okay, well, I tell you what. I see the fact that I do have a factor that is common to both of those denominators if I were to reverse the order of that second denominator. So I'm going to do that, and I can do that first or I can do that last. So I could actually turn that into negative cosine and flip those signs. And if I do that, I get sine squared x over cosine x times sine x minus cosine x. I get minus cosine squared x over sine x times sine x minus cosine x. Okay? Now, the problem is I still don't have a common denominator. And you might be thinking to yourself, no, please don't. Yes, I am. I'm going to multiply this one by cosine x over cosine x. I'm going to multiply this one by sine x over sine x. And that's going to give me sine cubed x minus cosine cubed x over the common denominator of sine x cosine x times sine x minus cosine x. Now, some of you who remember your difference of two cubes are already seeing where this is headed, because this right here is one of the factors of the numerator. That numerator factors into that. And those of you who do not remember your difference of two cubes, I would look that up. Okay, and since multiplication is commutative, I've simply flipped the order of the factors in the denominator. Now, these right here obviously cancel. This and this, if I put them next to each other, turns into 1. Okay, now I have two factors in the denominator, and that actually was several strokes of the pen, but that's still a monomial, so I can separate the fractions and simplify. And since addition is commutative, I'm going to put this over here, 1, I'm going to put this over here, times secant x cosecant, x, and that was what I was looking for all along. Now, just like I said in the last one, it is entirely possible that I did this the long way, okay? But I don't think so. And the reason that I don't think so is the fact that there is that basically this right here implies this ratio right here. The fact that there is a 1 as a coefficient in front of sine x and cosine x, and the fact that the 1 likely came from sine squared plus cosine squared, means that factorization from the difference of two cubes is really the only way that I can see that that comes about. I may be wrong, but I'm pretty sure. Now, that was nasty. But if you followed it, congrats, you have a firm grasp on what is going on. Now, having a firm grasp and understanding what's going on and being able to do it yourself, of course, are two entirely different things. But like I said in our class discussion today, time and exposure, time and exposure, time and exposure. So by all means, please do get to work on the homework. If you have any questions, please do shoot them to me. If you finish the homework and feel like you need extra practice, I have posted gobs of questions, including some solutions, in sort of a message tacked on to the assignment. If you have trouble, you shouldn't have trouble finding that. It's under posts in the general channel. But yeah, go ahead and shoot me a message, email, or chat if you need any further help on this. Otherwise, I will see you in class tomorrow. Bye.